Hello, Chemistry 2342. We're going to go ahead and redo some of the slides with some written annotation so that we can get a little better idea of what Chapter 17 is all about. Let me start to share my screen right here. And we're going to go over those Chapter 17 slides one more time with annotation, and so that we can all get kind of where everything's going uh, with all the different systems. So we're going to do Chapter 17, Part 1, and I'm going to call this A because I'm actually going to split it up into the previous section that I had before. But I'm going to splitting it up into going all the way down to the diacids, and then starting in the next section on the esters, okay? So the great thing about, carbonyl compounds is we've learned about them already in a couple other chapters. And so that we already know about the aldehydes and the ketones. Now, what's different about the aldehydes and ketones from the other systems is that those are only bonded to hydrogen and to carbon, and both of those are very similar electronegativity to that of carbon. In fact, this is a nonpolar bond, and then this is almost a nonpolar bond here. So the aldehydes and ketones have different reactivity than the carboxylic acid sets, okay? In the carboxylic acid set and derivatives here, we have a electronegative atom bonded to that carbonyl. So the simplest form of that is, of course, the carboxylic acid. And with the oxygen, we also have the ester and the carboxylic acid anhydride in that set. If we have a nitrogen on that set, they're called amides, and there's a couple different ways we can use that. In fact, there's a derivative of the amide, which we're going to call a nitrile. It's kind of a protected carboxylic acid, and I'll show you that in a minute. And then the last one we have is the acid chloride, or with the chloride system here. Okay. So let's talk about these carboxylic acid derivatives here. So just in general, if it's just the carboxylic acid, it has the OH group on there. That's the definitive factor that separates it from aldehydes and ketones. Okay. If we have a chloride on here, that makes it an acid chloride. Now, technically, you can have all the other halides there, but they're not as useful as they are very reactive and or not very stable. But the acid chloride is the most stable of the set, and so it's the most useful synthetically. Okay. The next one we can have is, it's like taking two carboxylic acids and just removing one equivalent of water. And that's why we call it the anhydride. It's a dehydration of that to give us this acid anhydride. And it has reactivity. In fact, both of these react just in air with water to hydrolyze down to other materials. The next two are a little more stable. If we have, instead of the OH group, we put an OR group on there, we now have an ester, and these are nice and stable in a lot of the different compounds we use. I'm going to move over here to the amides right here. When we have nitrogen, we don't have to have substituents on the nitrogen, but when we do, we can have them bonded to carbons or other carbonyls and call them other groups. So if they're just bonded to carbons or hydrogen here, we call them amides. Now, what you can also see is if we remove this oxygen and these two hydrogens, that's the removal of water, right? If we remove water from this amide structure, we actually end up looking at like a nitrile down here. Now, you can think about a nitrile as a protected amide, or a protected carboxylic acid, because we can make it and break it by just hydrolyzing it back to the amide or even back to the carboxylic acid if necessary. Okay. So when we talk about priorities and nomenclature, we started way back with just our alkanes. And we said, okay, if we have an alkane, we have it ANE. And then if we have a group attached to it, we either have the alkoxy group or the halo group. Remember, neither the ether nor the halide changes the parent name. So that's why we always started with the alkanes and then added ethers and halides to it. Okay, so in priority, if we have an alkane only, we have it with the ANE, then the alkyne takes precedent over that, and then ene. This is why we have the ene-ine and or ene-all systems here. Okay, next, if we don't have any other if we have any of these functional groups plus an amine takes the parent name. If we have any of these groups plus an alcohol, alcohol becomes the parent name. For example, ene-one or ine-all. Okay, Now, the functional group that takes priority above the alcohol is the ketone, and then the aldehyde, followed by the nitrile and amide. Remember, the nitrile is just a dehydrated amide, which is there. Then an esters up above that, and then the carboxylic acid derivatives take precedent. So if you have a nitrile on a carboxylic acid chain, what you're going to end up using the nitrile because it is not changing the parent because it is has a lower priority than the carboxylic acid. We have to say that's the cyano-substituent. So if we have aldehydes on the system, and it's right at the end right here, we call that the formyl group. But if we have ketones, we would call that an oxo-substituent on any of the ones above it. Again, the hydroxy, amino, ethynyl, ethynyl, alkyl groups would be those substituents as well. So we'll go do that as in some of our practice problems. Okay. So moving on, when we're naming carboxylic acids, we have to look at the longest chain containing the carbonyl of the OH here. So we would start, because that's changing the name, we always start numbering from there. And in this case, we go 1 through 6 right here. So that's going to make this hexanoic acid. Okay, so we have a hexane from the 6 carbons. We drop the E and add oic acid. So this one becomes hexanoic acid. Okay. So in this case, we have 1, 2, 3, 4 carbons in our chain, and we start from here. So that's going to make it butanic acid. So it's butane, oic acid, butanoic acid. But this is an ether right here, and so our substituent has to be placed on there correctly. And so since it's an ether, it's the methoxy group. And it is, because we always start numbering from that carbonyl, this is the 2 position. So that's where we get the 2-methoxybutanoic acid. Okay. Now, whenever we have ring systems like phenyl groups or even the cyclopentane ring, we use the cyclopentane as the parent, and then this is our substituent, which we name it for. So what we'll do is we'll name it cyclopentane carboxylic acid. Okay. So, but now, because we're naming it for the carboxylic acid, that immediately becomes our 1 position. So that makes it our 2, our 3 position. So that's why it's 3-methyl cyclopentane carboxylic acid. And of course, this one is going down and this one's going up, which is where we end up with our trans. So all the other rules of nomenclature apply. It's just that if you see a carboxylic acid on your system, that's what you're going to name your compound for. And then that's also where you start your numbering system from. Okay. So let's look at some common names for the acids that we have. So if we were to name this by a nomenclature name, we only have 1 carbon, so that's going to make it methane. So we'd call it methanoic acid. Again, 2 carbons, ethane, ethanoic acid, etc. And all those follow that simple rule until we get down to the benzoic acid right here. So the benzoic acid here actually follows the cyclic system. So we have benzene with the carboxylic acid as the pendant here. So we're following the rule with cyclics and our system. But these also have some common names. So before this was called ethanoic acid, it was actually Latin for the vinegar or acetic acid. This one right here, if you think about it, looks a lot like formaldehyde, which is the dialdehyde here. And so if you're just oxidizing one of these hydrogens to make it there, that's why it's formic acid. So it's based on that word formaldehyde. So then this is fairly similar, propionic acid. This right here, it starts with a B, but it's butyric acid. And this is gets its name from this odd smell in the rancid butter. Then we have valeric acid. This is a common one with the 5 carbons in the chain. With 6 carbons in the chain, we get up to caproic acid. And with benzene, we call this benzoic acid as the common name. So once we get to diacids, we also have some stuff to worry about there. If you look at the common name here, it's called oxalic acid. And remember, we use oxalyl chloride as one of our reagents in the Swern reaction. So that's where that comes from. But if we looked at its common name, we have 1, 2 total carbons. So that would mean ethane. And then we have to say dioic acid at the end. So it's ethane, dioic acid, but the common name is oxalic acid. Here we have 1, 2, 3 uh, carbons in the chain, so that's propane dioic acid. 1, 2, 3, 4, and that's butane dioic acid. So that's how you would name it in the structured system. Now, if we think about these as the fact that they are carboxylic acids, which means we can deprotonate them and make them into salts, we name that slightly differently. And what we do is we name it as the carboxylate anion. And so that's where we get the word 8 out of it. And so what we would do is we would take the name of the metal, so potassium, sodium, etc., and then the parent name in a UPAC or common, and then we add 8 to the end of it. So in this case, we have 1, 2, 3. So our parent is propane. So we have propionate. So this is potassium propionate right here. So that's how we name salts. Let's go back and name some of the common names for those dioic acids, though. They have a kind of an interesting system in which they're used on. So if we were to look at this right here, this only has a single carbon. So its systematic name would be methane dioic acid. So we had ethane dioic acid, propane dioic acid, butane, etc. So that's where our common names would come from. But this is called carbonic acid. So this is basically CO2 and water. In fact, it decomposes quite readily to give us that. The common name for this is oxalic acid, then malonic, succinic, glutaric, and a diptic acid. Once we get to the benzenes, the common names for the benzenes that have 2 carboxylic acids on them, now that's called the phthalic acid, okay? So notice this is ortho, or the 1,2 derivative here. If it's the meta, it's actually called isophthalic acid. And if it was the para over here, we call it the terephthalic acid. So we would name them that way. But our systematic name would be benzene 1,2 dicarboxylic acid. This would be 1,3 dicarboxylic acid, and this would be 1,4 dicarboxylic acid. Now, the way to remember the common names for this is to say, starting with just 2 carbons, you have, oh my, such good apple pie. And that would give you oxalic, malonic, succinic, glutaric, adiptic, and phthalic acid. Okay, so what I'm going to do is I'm going to stop this here, and then I'm going to go for chapter 17, 1, part B.